Okay, in this video we'll talk about Fourier series and in particular trigonometric Fourier series formulas. This was originally intended to be the last little bit of the video that talks about complex exponential Fourier series formulas, but I got long-winded, so in this one we'll concentrate only on trigonometric Fourier series formulas, except when we show the relationship between Fourier series coefficients for trigonometric formulas and the complex exponential Fourier series coefficients. So let's go to our periodic function. This is a periodic function. It's periodic with fundamental period t0. It has a radian frequency omega 0 of 2 pi over t0. Okay. Now it turns out that we can represent this periodic function as the sum of sines and cosines. And the formula for doing this is the following. X of t is equal to a coefficient a0 over 2. You'll actually see that called different things in different books. Plus the summation from k is equal to 1 to infinity of a sub k cosine omega 0 t plus b sub k sine omega 0 t. And a sub k and b sub k are the trigonometric Fourier series coefficients. Okay. You can compute those. Typically, as in the previous video, you're usually given x of t, and you want to compute the Fourier series coefficients from x of t. So it turns out that a sub k can be computed as 2 over t0 times the integral over one period of the function. So this can be any period of the function. You can start at 0 and go to t0. You can start at minus t0 over 2 and go to t0 over 2. You can set this up any way you want to, as long as you integrate over exactly one period. X of t cosine omega 0 t dt. And the b sub k's are defined similarly, except that instead of multiplying x of t by a cosine, you multiply it by a sine. Okay, so, and a0 is I believe 1 over 2 over t0. This is going to be a0 integral over t0 x of t dt. So a0 is essentially the DC value of the signal. So these again, basically the idea is we've expressed x of t as the sum of a set of cosines and sines. There are some interesting things that occur if x of t is even. Then all of the b sub k's, the coefficients in front of the sines, are 0. This makes sense because cosine is an even function, and so you would expect an even x of t to be composed of even sinusoidal things. If x of t is odd, then the a sub k's are 0. And again, this makes sense because if x of t is an odd function, then the sine is an odd function, and that you would expect it to work out that you can compose an odd function as a sum of sines. So this is the trigonometric Fourier series. Now, the next part of this video is going to assume that you've already looked at the complex exponential Fourier series video. If you haven't seen that yet, I'm sure your time would be well spent to look at that, because it turns out that there's a very nice relationship between the trigonometric Fourier series coefficients and the complex exponential Fourier series coefficients. So I'll write that down. We won't spend any time deriving it, although it's quite fun to derive. It turns out that the cosine coefficients, the a sub k, are equal to 2 times the real part of c sub k, where c sub k is the complex exponential Fourier series coefficient. b sub k is equal to 2 times the imaginary part of c sub k. And I was afraid I'd do that. There's actually a negative sign there. And so there's this relationship between the real and imaginary parts of the complex exponential Fourier series and the coefficients of the trigonometric Fourier series, which, if you go back and look at the even and odd, what happens to c sub k and a sub k and b sub k when x is even or x is odd, you'll see that things happen the way they should, in the sense that real parts of c sub k or imaginary parts of c sub k go to 0. So this basically concludes the discussion of Fourier series. I will, in a subsequent video, show how to actually go ahead and compute c sub k for a particular video, or for a particular function, particular video. I have no idea where that came from.